Today I'm just going to do a couple of examples for you that you can find in section 2.8 in your notes about calculating the average atomic mass. So the first example is that you have chlorine and has two naturally occurring isotopes, chlorine 35 and chlorine 37. Using the data provided in the table below, determine the atomic weight for chlorine and tell me how that compares to the value on the periodic table. So to do this problem, we need to use the equation that's on the previous page, that the mass is equal to the sum of your fractional abundance times the atomic mass. And so for this particular problem, that's going to be the fractional abundance of chlorine 35, which is 0.7590, times that isotonic mass, which is 34.97. And then this sum means that we're going to add each of those quantities together. So it'll be plus the same thing for the chlorine 37 isotope. So for that one, it's 0.2410 times 36.97. And if we multiply all that out and add it together, we end up with 35.45, which is the same as the mass that you'll find on your periodic table. All right, the next example is using the information we have on the periodic table to figure out the isotopic mass of an isotope. So if boron has two naturally occurring isotopes, boron 10 and boron 11, use the data provided below to determine the fractional abundance and the isotopic mass of boron 11. So we're going to use just a little bit of common sense and then also the equation we just used in the previous problem. So if there's only two isotopes and one of the isotopes is 0.1991, then the fractional abundance of the other one has to be that one minus that number. So that would be 0.8009 for the fractional abundance for boron 11. All right, and now to figure out the isotopic mass, we're going to have to use the mass on the periodic table. So if you look at your periodic table, the mass of boron is 10.81, and that's going to be equal to the fractional abundance of boron 10, which is 0.1991, times that isotopic mass, which is 10.0129, plus the fractional abundance of the boron 11, which we just said is 0.8009, and then X is going to be the isotopic mass of boron 11, which we don't yet know. All right, and the reason we don't know this, it's obviously going to be close to 11, so you're going to know if you got the answer close or not. But if you remember, the masses of the proton, neutron, and electron are not, or the proton and the neutron, are not exactly 1, and so that gives you a slightly different number than just 11 even. So if we multiply out this part here, we get 1.994, and then that'll still be plus 0.8009 times X. All right, and if we subtract that on both sides, we get 8.82 equals 0.8009 times X, and therefore X is equal to 11.01 AMUs. All right, so those are two examples. We're going to do more examples like this in class, and you can find some examples in your textbook as well.